about the nervous system. So I will do my best to keep it as applied and simple as I can. There is some a little more complicated stuff in this chapter, I think, but you can manage it, I know you can. And just ask questions if I'm not making things clear, let me know. I will be going quite fast through the kind of anatomy layout information because that should be reviewed for you from A&P. And if you don't recognize it or you don't, you're like, I know we did that, but I don't remember it, then please make sure that you go back and review it, all right? Let's see. Got all kinds of fun stuff going on with PowerPoints. Let's see what's happening today. That's up. Did that switch to the main slide? No? I don't understand what's happening. When is this going to correct itself? There's all these new little glitches turning up. Okay. I'll keep it small. So you'll note that points 2, 3, and 4 here are grayed out. That's because you need to understand the organization of the nervous system. You need to know which element of the nervous system is responsible for what kind of job. But there's not going to be a question on what does a neuron look like, and there won't be a picture of a neuron that you have to label or anything like that, right? So you have to know that stuff because otherwise the rest of it doesn't slot into place, but it's not going to be on the next exam. So our very advanced nervous system is one of the things that separates us, distinguishes us from lower vertebrates and insects and fish and other things like that. It allows us to have a conscious awareness of our surroundings and of ourself. So that's something that's quite unique to higher vertebrates, is that they can recognize that they have a self. It's responsible, in our world, what we're interested in, it's responsible for initiating all the movements that we do and for maintaining homeostasis, which is really important when we're exercising or being physically active, because we get huge disturbances in our internal systems when we're doing high levels of exercise. Right? So we have to be able to recognize that, respond to it, and then when the exercise is over, bring the body back to what's typical at rest. So the fancy word for bringing us back to level is homeostasis. It means that we are able to maintain the balance of the systems by adjusting our physiology and maintaining systems within certain limits. So we have very kind of quite strong boundaries on most of these physiological systems. And so when we upset them, when we're exercising, we have to bring them back into those boundaries. So some of the challenges that we see are things like an increase in temperature, right? And it's not just an increase in, oh, I feel hot because I'm putting my hand on my head. It's an increase in your core temperature that can lead to some really quite significant health issues, all right? We've already talked a little bit when we were doing the energy systems about the fact that when we are making ATP, depending on which system we're using, we may be producing acids and changing the environment within the muscle cell. That has to be brought back to balance, right? Exercise can lead to hypohydration if I'm not paying attention to how much fluids I'm drinking, right? We see a lot of change in blood pressure when we're exercising, particularly if we're doing resistance or weight training type work. And we see changes to blood glucose levels. So the body has to be able to detect those changes and then respond to them appropriately. All right, so we've got a big job for the nervous system to do. And it achieves many of these ideas, bringing these systems back to homeostasis, back to resting levels, by using feedback systems. So the feedback system can communicate between the organs that are producing hormones and things like that and the nervous system. And there are two main types. One is a positive feedback loop, so that promotes a particular process. So the example that the book gives us is that we get an increase in acidity if we're working under our 3 minutes and we're using glycolysis, right? And then we see an increase in blood flow. The more activity we do, the higher the levels of acidity and the higher the levels of blood flow to try to wash that lactate out of the muscle and drop it off to the liver or somewhere else. Okay. Then a negative feedback loop, instead of promoting the process, kind of squashes the process, right? It's responsible for bringing the process back to the resting level, okay? So the increase in body heat is a simple example. If your body temperature rises, you'll start to sweat. That sweat evaporates off your skin and is responsible for cooling, right? We want to cool the body, cool the blood, so we bring the blood to the surface, we start sweating, the sweat evaporates off our skin, and that cools the skin down and cools some of the blood down, right? So regulating the physiological functions that we use during exercise requires lots of different loops, right? There's many different loops occurring. Okay, so this diagram is of a neuron. If you look in your book at chat, where's that diagram? Look at page 83. Figure B shows you lots of different types of neurons. Okay, this diagram is a schematic of just an average, right? They don't all look like this. It depends what their job is, right? So we have our dendrites. So our dendrites are responsible for receiving the information, so the impulse from the previous cell, and then they transmit that impulse to the cell body. Around here, it's not labeled on this diagram, but we have the axon hillock, And the axon hillock plays an important role because it summates all the impulses that are coming in from the dendrites. And if we reach a certain threshold, then it will send a signal on and we get an action potential. Okay. So the hillock is around here. And then if we reach threshold, right, we have enough stimulus coming in, it will initiate the impulse on down the axon to either the next nerve cell, or in our case, we're interested in looking at motor nerves, and so it's the end of the axon is going to synapse with the muscle fibers. So the action potential is the fancy name for the electrical signal or impulse that's being transmitted. All right. So as I said, there's several different types, structural types of neurons, and you can look at some of them in that diagram on page 83. But we're interested in the functional types because we're looking just really at motor nerves. Okay? So our functional types are sensory nerves, and they're responsible for taking the message from a sensory organ and transmitting it to the central nervous system. And then we have motor neurons, which are responsible for taking the message from the central nervous system to the muscles. All right? Now, motor neurons are interesting because the cell body is within the spinal cord, and then it has a really long axon that stretches out to innervate and synapse with which particular muscle it's got to synapse with. So just imagine if you've got like a 7-foot basketball player, then the motor neuron down to the muscles around the ankle, the axon is leaving his spine and running all the way down to the ankle. So the axon can be very, very long. If it's just going to the muscles of the core, that axon's going to be shorter, right? The dendrites are relatively short because they're inside the spinal column, and they get impulses from the motor nerves that are running down from the brain, right? And then we have a kind of phony nerve called an interneuron, and they can sit inside the spinal column and connect, they kind of transmit information between sensory and motor nerves. The other types of cells that we see in the nervous system, about 90% of the cells in the central nervous system are what we call neuroglia. And neuroglia are responsible for providing the sort of the padding, the support system, and they provide nourishment to the nerve cells. Right? They also form the myelin sheaths that we see around motor nerves and some other nerves in the body, but we're particularly interested in the myelin sheath around a motor nerve, because the myelin sheath increases the velocity at which the signal can travel down that axon. You know, and it wouldn't be very good if I'm sitting at the traffic light and I see the traffic light change and my brain says, okay, press the accelerator, and it takes forever for that signal to get to my foot and press the accelerator. Right? But that signal can travel really, really fast because motor nerves have these myelin sheaths, and we'll talk a little bit more about those. And then the synapse is the junction, right? So the synapse is where the dendrite would be the receiving side of the synapse, and the axon of the previous nerve would synapse with the dendrite, right? So if we're looking at a motor nerve, then the axon of the motor nerve synapses with the muscle fiber, and that's called a neuromuscular junction. It's just a specific type of synapse. Right, so you can see here, here's the axon from the previous. This is the little kind of cartoony version. If you like to look at something that's a little more realistic, you can go back to page 83, and there's a very detailed diagram of a synapse. All right, but I like the cartoony version. It's nice and simple. All right, so here's my axon from the previous nerve, and at the kind of tips of the axon, there are these little vesicles that store a chemical substance called a neurotransmitter. And when the vesicles are stimulated, they release the chemical, and it can float across the gap to get to the dendrite on the next, or the muscle surface of the next excitable cell. Right? So we have receptors on the post side. Right? So we've got two excitable cells. We've got an electrical signal coming down the nerve. We have a little gap, the synaptic cleft, and the electricity can't travel across the gap. So we have to turn the signal into a chemical signal to move across the gap and attach to the receptors on the postsynaptic excitable cell. Okay. So the neurotransmitter is the chemical. It attaches to the receptors. If there's enough neurotransmitter binding to the receptors on the next excitable cell, then we see the action potential reignited and the electrical signal continues. So we go electrical, chemical, electrical. When we are at a neuromuscular junction, this neurotransmitter, this chemical, is acetylcholine, which is shortened to ACH. Right? So ACH plays an important role from a movement perspective, because without it, that signal from the brain couldn't get to the muscle. The receptors on the postsynaptic cell are made of proteins. This is another use for protein that isn't to do with energy, right? The receptors are proteins, and they have specific shapes, and they will only bind with one particular substance. So that could be a hormone. We have hormone receptors, so like in our hippocampus, right, when we get stressed, we release loads of cortisol. The cortisol is a stress hormone, can attach to the receptors in the hippocampus and turn our memory off, right? Not very useful when we're trying to study, okay? So that receptor, that protein, can be a receptor for a hormone or for a chemical, but they're very unique. They will only accept the attachment by the molecule they're shaped for. Okay? So each neurotransmitter throughout the body has its own particular kind of receptor, and that's good because we've got all these chemicals flooding around all over the place. If the receptor could attract any chemical, then the rest of the process might not work properly, right? So each receptor is very specific, and that allows for accuracy in transmission of information around the body. Right? When the neurotransmitter binds with the receptor, as I said, if there's enough neurotransmitter, then we open a channel and we initiate another electrical signal. And the electrical signal is initiated, as we'll see, probably Monday, by the, Monday? Maybe we'll get there today, by moving charged ions backwards and forwards across the membrane of the cell. Okay. So at this point here, when we open the channel, we're turning the signal back into an electrical signal from a chemical signal. Okay. Typically, receptors will only allow one type of ion to go through a channel. It so happens that when we look at the neuromuscular channel, neuromuscular junction, the receptors allow two. They let both sodium and potassium move back and forwards. Any questions?
None so far.
Okay, thank you, Kayla. Okay, so this is in your textbook, this diagram, and it gives you an overview of the nervous system and the different sections of the nervous system. So you need to recognize these, right? You've got to know the difference between the autonomic and the somatic or sensory, right? The central and the peripheral nervous systems. Okay, so again, you're not going to have to reproduce this or do anything with this in the exam, but if you don't understand this, then you're not going to understand the process of how movement occurs. Okay, so again, I'm going to go relatively quickly. Yell at me if you need me to repeat something or explain it a bit differently. All right. The central nervous system is composed of the brain and the spinal column. Anything outside of that is peripheral nervous system. Okay. So in the brain we have the cerebrum, which is this large area here, and that's the seat of what we call consciousness, right? This is where decisions are made, signals are interpreted, behavior is driven in here, our motor cortex is in here, right? And so we call it the seat of consciousness. And it's really interesting to note that the central sulcus, which runs about here, right, which is like a channel, okay, on one side of the central sulcus is the motor cortex, and on the other side is the sensory cortex. That's really key, right, that we evolved that way, because that means that the sensory information and the motor response to that information are very close together, and that allows us to respond quite quickly to sensory information, right? If the motor cortex was all the way over here, the sensory cortex was all the way over here, then it would take a long time for the sensory cortex to talk and send information to the motor cortex, okay? Then the cerebellum is down the lump at the back here. All all right? And the cerebellum is responsible for the fine-tuning, the kind of coordination. So the motor cortex initiates the movement, but that signal has to pass through the cerebellum, and it will tweak it and fine-tune it and make it more coordinated if it needs to. Okay, the brainstem is in here, and it's responsible for regulating our heartbeat, our breathing rate, our blood pressure, the reflexes. Okay. So our brain is obviously crucial, and right now in sport we've got a big media push and a lot of changes to rules and things that are happening because of damage to the brain that's occurring when we're taking part in sport. So in particular, at the moment, American football is under the radar because of the number of concussions that football players receive. But also soccer players get a lot of concussions, rugby players get a lot of concussions, gymnasts get quite a few concussions, right? So it's not just American football, but the problem is that with American football that they seem to be so regular, and there doesn't seem to be any question about putting this player back in the game, or now we're getting better at letting them rehab, but then they go back and get another one. Once you've had one concussion, you're much more susceptible to another concussion, right? So, and then obviously the more concussions you have, the more damage there is occurring. So it doesn't always mean that the athlete is going to black out. So you have to keep your eyes open when you're watching, when you're coaching your athletes. If they fall and hit their head, or if they're in a contact sport and they're getting hit, this is important because our brain is very, very delicate tissue. It's really, really soft. And it's housed in this nice hard casing with only a tiny, tiny little gap with some fluid in it. So when you take a hit to the head, right, the brain can bobble around a little bit in that space and bang up against the inside of the skull and get bruised and get damaged, right? So we have to take very good care of it, right? Symptoms of concussion can be delayed, so you could watch someone take a fall, hit their head, they seem fine, and then later on they start to experience dizziness, or they might start feeling nauseous, they might find they can't sleep properly, their memory and coordination seems a little bit off, right? So many concussions over time can result in some pretty horrendous problems. So there's some link to developing epilepsy, there's links to depression, and we're seeing quite a few athletes commit suicide that they then link back to depression that's been caused by concussion, because some of the athletes' families will donate the body and allow people to look at the brain, and then they're seeing very specific damage in areas of the brain that would have led to depression and led to them committing suicide. Alzheimer's and Parkinson's are both being shown to be possibly linked to concussions, so later on in life these athletes are developing Alzheimer's. And I have an article up for you to read on Blackboard. It's called "Why is it so hard to stop sport concussions?" And one of the things that the article discusses is the fact that better helmets right, which are being developed to try to keep the athletes safe, may actually be making things possibly worse because the athlete feels safe, they tackle harder, right? And then they hit their head or they hit the other person's head harder. Now, I know there are rule changes in American football to try to get tackling lower, so if you go in high, you get a penalty, but the damage is still done, right? So if your coach has told you win at all costs and you tackle high and you get kicked out of the game, but your team wins the game because you took that person down, right? Then the damage you did to that person becomes kind of supported, right? So I think we have to have a real change of affect around how dangerous is this, right? Are we willing to accept this? Okay, particularly with high school kids, right? I mean, high school kids are leaving, high school football players are leaving high school and coming into the college system, and they've already got 2 or 3 concussions on their sheet. Right? Okay, so the spinal cord is the other part of the central nervous system. So this bundle of nerves that runs down from the back of the skull here through the foramen in the spinous processes, all the way down, right? The vertebra enclose it. So again, these nerves in the spinal column have this hard casing surrounding them to protect them. And then all the way down we see nerves coming out from the spine to different organs in the body. So we also see reflex actions occurring in the spine. So it's possible for a signal to come to the spine, turn around and go back out to the muscle without having to come up to the brain, which is important in sports because we have to be able to react very, very quickly, all right? And it allows, the reflexes allow us to respond very fast to things that are happening in our environment. So for example, if you watch, if you Google cricket and you watch a cricket catch that's very close to the bat, right? So if the wicket keeper dives and catches the ball, that's in such a fast period of time that that can't be centrally processed. Right? Same with baseball, right? Someone swinging and hitting a baseball, that's too fast for them to have consciously controlled that action. So we also have to take very good care of our spinal cord, because if we damage this, depending at what level we damage it, we can lose function below where the damage occurred, right? So we want to be very, very careful. So this diagram...
Dr. Well, I have one quick question.
Oh, go on.
So, when people have spinal cord injuries, what is it that makes it so difficult or impossible to fix? I've always wondered that.
Oh gosh, big question. So, depends where the damage is and what the damage is. So, some people can get an injury where the vertebra collapses and squeezes on the nerve, and so they lose feeling from that pinch. It's more than a pinch, but right? Now that can be fixed by going in and inserting some, either putting pins in or inserting some rubbery type substance to spread the vertebra back out again and release the nerve. If they have an injury where they sever the cord, for example, that can't be fixed to my knowledge. I don't think that nervous tissue mends. It doesn't rejuvenate in that way. So then, depending on where that break, that, you know, if the sever has occurred, will depend on how much paralysis the individual has. And one of the really interesting lines of research right now that many people are very anti, but it's friggin' amazing to be honest, is looking at stem cells, because what they've been working with people who have paralysis, because the central nervous system doesn't regenerate, but they can take stem cells and make new nerve tissue. And so they're working on trying to like regenerate the thing that got broken. So there has been some progress. There's been some progress with people being able to move a leg with some electrical stimulus help. I mean, it's got a long way to go, but it's quite amazing to watch. And I've seen film where they've got like electrical boxes on the patient's back that are sending electrical impulses to the muscles of the leg, and that person is able to stand up and take a step. So, is that fixing the original problem? No, but it's at least providing a modicum of independence and, you know, being able to be upright. I'm not sure if I'm answering your question, Kayla.
Oh no, you are. I was just wondering the difficulty behind it. I didn't know what the difference was between like fixing normal tissue and then fixing something so delicate like the spinal cord.
Yeah, it just, I believe, I could be wrong, but I believe it's that nervous tissue, neurons don't regenerate. So once there's that kind of sever in the cord, I mean, you've got so many nerves in there, and they all do different things. That's what I believe, but I could be wrong. But the stem cell stuff and the electrical box, the work that they're doing in hospitals that are specifically geared for paraplegics and things like that is amazing. Yeah, needs lots of support, in my view. Coming from a sport where broken necks are not unheard of, unfortunately, right? And quite unfortunately, many gymnasts break their necks and end up paralyzed, depending where the break is, or break their back. So, okay, back to this diagram. So this is a picture of a knee tap reflex, which you've probably heard of. It's what we call a monosynaptic reflex, and that's because if you look here, then and we haven't talked about muscle spindles yet, but we will. All right, when we tap the patellar tendon, we stretch the quadricep a little bit, and that stretches the sensory organ, which in this case is a muscle spindle, sends a signal to the spinal column, and it synapses immediately with the motor nerve that comes back to the quadricep and causes a contraction in the quadricep. So it's called a monosynaptic reflex because there's just the one synapse involved. okay? And so that then we get the contraction and we get the leg kick, okay? Now, simultaneously, if you think about it logically, right? If I'm sitting on the end of a table, right? And my quadricep contracts and I see my foot go, then what had to happen to the hamstring? Right? If my quad contracts and my foot kicks up, is my hamstring contracting?
Wouldn't the answer be yes?
I wish it was for you, Kayla, but no. Right? Because if the hamstring's contracting at the same time, then that lower leg isn't going anywhere. Right? So the hamstring has to relax. And so what we see in the reflex is the sensory nerve has this monosynaptic connection to the motor nerve back to the quadricep, but then it passes as well through an interneuron to the motor nerve for the hamstring, and it turns the hamstring off so that we get a reflex kick. I can't remember if any of you are physical therapy or athletic training students. If you are, there is information on page 92 about how you grade a knee tap reflex. You have to score it if you're the therapist. So the rest of us don't need that information, but if you are going on to therapy school, that information is there for you on page 92. Okay, now, this is a diagram of what they call reciprocal innovation. And I have to say, I could be wrong, but I think the diagram is incorrect. So I am going to try and draw the little bit that's going on in the spinal column for you. So what we're looking at is that we get the sensory information coming to the spinal column, and then we get both facilitating and inhibition occurring in the spinal column. So the sensory nerve synapses with a facilitating interneuron, and that then synapses with the motor nerve, in this case for the quadricep, and stimulates the quadricep to contract. But that sensory nerve also synapsed with an inhibitory interneuron, which turns the action of the hamstring down. So the example that they're giving you here is like a lift pull of the bar, right? So if my quads are going to contract and extend my legs, then my hamstrings have to either turn off or at the very least turn down and allow my legs to straighten up as I lift the weight up, right? What's interesting about reciprocal innovation is that they see training effects here. So that it looks as though this kind of innovation, this kind of dual-sided information to the muscle groups is improved with training. So let me see if I can draw what I think's happened. They've used this same little diagram here in the spinal column as they did on the reflex picture, and I think they missed out an interneuron here. So, let me see if I can draw it. This should be funny. Let's give it a go, see what happens. They use red, so let's use red. So the sensory nerve leaves the muscle, oops, and comes into the spinal column. And then there should be, and there's the cell body for the sensory neuron is out here in the bit that sticks off the side of the spinous body. All right. So then we should have an interneuron that we call a facilitator interneuron that synapses with the motor nerve back to the muscle. Okay. But we also have that's the wrong colour. We also have what we call an inhibitory motor interneuron, which synapses with the motor nerve for the hamstring. It's not a very good diagram, I'm sorry, but I think you can see where I think that they've made a mistake on the diagram in the book, because they're missing that facilitator interneuron in that diagram. So this one here. Right, so this is the facilitator, and this one is the inhibitor. Okay. So when you read that through, if you think about this diagram, I think it will make a bit more sense when you're reading the explanation in the text and you're looking at the diagram. Just think about, oh, it's missing that facilitator interneuron. Oops, let's go quick. Okay, peripheral nervous system. Anything outside the brain and the spinal column is divided into autonomic and sensory. Okay. The autonomic nervous system is responsible for unconscious function. So our heart rate, our blood pressure, typically our breathing, although we do have some voluntary control over our breathing, but typically our breathing is controlled involuntarily. Digestion, right, things like that. So this unconscious side of the peripheral nervous system is also divided into two. We have our sympathetic nervous system that's responsible for what we call fight or flight, right? It's responsible for getting the body ready to deal with something it's perceiving as dangerous, typically. All right? So we get an increase in heart rate, an increase in blood flow. We divert the blood flow away from the kidneys and the digestive system, and we divert it towards the muscular system. It stimulates the liver to break down stored glycogen and pump loads of glucose into the bloodstream. And it's triggered by something that is perceived as stress. So that stress can be exercise, which is typically a positive stressor up to a point, or that stress could be something very dangerous, right? It could be excitement, so, you know, right before a competition, your heart rate's going, you're starting to sweat, right? But you're excited to get into the competition. You're not scared of the competition. But if you walk into the forest outside Ruidoso and you're confronted by a bear, your body is going to do the exact same thing as it does when you're getting excited about your competition, right? The physiological response to stress is exactly the same. It doesn't matter what the stressor is, okay? The other part is our parasympathetic nervous system, and this is the part of the unconscious, the autonomous nervous system that's responsible for bringing us back down. Okay, right? My heart rate has to slow down, my body temperature has to come back to normal, I've got to bring my blood pressure down, I've got to re-divert that blood flow away from the muscles back to the skin and the organs, right? Bladder function returns, rest and digest. Okay? So on Monday we will just quickly go over the sensory system very quickly and look at some fatigue issues, and then we will start on motor neurons. Okay? Questions? I said I was going to go a little bit fast. I know I did go a little bit fast, but as I said, a lot of that should have been review for you guys because you've all got A&P. Okay, so make sure to go back and look at it if you couldn't remember all the divisions that I was throwing at you. Okay. Monday, hopefully, we will be able to get through the rest of chapter 4. All right? So take a little bit of time, just half an hour or so, to look over this first part of the chapter so that when we move on Monday, you're not kind of floundering in quagmire. Okay? All right, so have a lovely weekend. Tomorrow is meant to be a beautiful day, not very windy, lovely and sunny. So enjoy, get outside. Have some fun in the sun, stay safe, wear your masks, and I'll see you on Monday.